Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the graph theory. So graph theory is another approach to carry out the network analysis. So first we will discuss various terminologies that are being used in the graph theory. And the last we carry out the matrices used in the graph theory to solve a given network. So what is graph in a graph theory? So basically graph is defined as a collection of branches and nodes in which each branch connects two nodes. So network is given. So identify the number of branches and number of nodes in the network and just simply draw the line representation of the network. So what is branch? When each network element is replaced by a simple line segment called a branch or an edge. Then path is the sequence of branches traverse in going from one node to another node is called path. Then what is connected node? Connected node is if there exists at least one path from each node of a graph to every other nodes. The graph is said to be connected, otherwise disconnected. Then what is isomorphic graph? Two graphs are said to be isomorphic if there is one-to-one correspondence between the branches and nodes of the two graphs. Then what is oriented graph? So if a graph carries orientations is called an oriented graph, and by convention, how will orient the graph? Then we have to follow some conventions. So by convention, the tail of the arrow for the current reference is put at the plus sign of the voltage difference. Suppose this is a voltage source and this is the direction of the current. It is moving from plus to minus because you know that the current flows from higher potential to lower potential. So in the graph theory, or if you are going to draw the graph of this branch, so branch will carry this orientation, okay, in this way. So we follow some conventions while drawing the oriented graph from a given oriented network. Then we have the another terminology that is being used in the graph theory, that is the degree of the node. So degree of node is nothing but it is the number of branches incident at a node of a graph is called degree of node. Then another terminology, that is the simple node. So a node of degree 2 or more is called the simple node. Then terminal node, a node is of having degree 1, means there is only one branch incident at that particular node is called a terminal node. Then we have the subgraph. So subgraph of a graph, say original G is a graph whose branches and nodes form a subset of the branches and nodes of the original graph G. So if you are required to draw the subgraph from the original graph, then we take some branches and nodes from the original graph and we draw the subgraph. Then what is proper graph? So a subgraph of a graph is said to be proper subgraph of graph G if it does not contain all the branches and nodes of the original graph G. Then a spanning subgraph, or we can say the spanning tree. So if a subgraph contains all the nodes of the graph G, it is called a spanning subgraph of graph G. Then planar graph. So a graph is said to be planar if it can be drawn on a sheet of paper such that no two branches cross each other. Otherwise the graph is said to be non-planar. Then complete graph, a graph in which there is one and only one branch between every pair of nodes is called a complete graph. And the number of branches in a complete graph having n nodes is given by n into n minus 1 upon 2. So these are the some terminology that are being used in the graph theory. So just we define. Then the another term that is associated with graph theory is tree and co-tree, that is the complement of a tree. So what is tree? So it is defined as a connected subgraph of a connected graph. which contains all the nodes of the original graph but does not contain any loop. So in a tree of a graph, there is one and only one path between every pair of nodes. So this is the definition of tree. So the branches of tree are called twigs, and the branches removed from the graph in forming a tree are called links. So the questions may be asked, what is tree, what is co-tree, what is twig, and what is links. So they are the definitions of these four terms: tree, co-tree, links, and twigs. Then set of all links corresponding to a given tree is called a co-tree or complement of tree of the graph. So there exists a co-tree for every tree of the graph. A tree may or may not be connected graph and may or may not contain loops. So these are the definitions of tree and co-trees, links, and twigs. Suppose if the graph has n nodes, so its tree will have n minus 1 branches. That is called twigs. Thus the number of twigs on a tree is n minus 1, and number of twigs n minus 1 is known as the tree value of the graph, and the number n minus 1 is also known as the rank of the tree. So in this slide, what is tree, what is co-tree, what is the link, what is your twigs, then co-tree, and in addition, what is the tree value of a graph and what is the rank of the tree. So we can find out the tree value and the number of rank of the tree using these formulas. So the number of links, say this is L, corresponding to any tree of graph is L is equal to B minus T. And what is B? B is the number of branches and T is the twigs. So B minus branch minus twigs. So number of branches in the graph and T is the branches of the tree, and branches of tree is equal to the n minus 1, where n is the number of nodes in the graph. So basically the link is B minus n plus 1. It is defined for a particular tree. Remember, the link and twigs are applicable to a particular tree or co-tree, you can say. Then come to the, basically these two slides are about deals about your terminology that are being used. So definition is very simple, you can visualize, you can easily remember. Now the most important thing is the matrices that are being used in the graph theory to solve a given network. So first we will discuss about the incidence matrix. So what is incidence matrix? So for a given oriented graph, it is easy to tell to which branches are incident at which nodes and what are their orientation relative to the node. So this information we can obtain from a incidence matrix. So this incidence information of the branches, of the graph can be given in a concise mathematical form by a matrix. So it is called incidence matrix. So incidence matrix gives the information of the branches of the graph and their which branch is incident at which node. We can obtain we can just write all the information in a very concise mathematical forms. So suppose for a given oriented graph having n nodes and b branches, the complete incidence matrix AA. So A and A, this small a, this subscript small a is defining includes all the nodes. Okay, is a rectangular matrix of order n into B, where n in the number, n is number of branches, B number of nodes, and B is the number of branches, where the column of the matrix correspond to the branches and column the matrix corresponds to the branches and the row, and the row corresponds to the nodes. So if there are n number of nodes and B branches, so in the matrix there will be n rows and B columns. Simple. So transformation from the oriented graph into a mathematical form. So in matrix, row becomes nodes become row, and the branches become columns in a matrix. Then what are the entries? Suppose this is the entry Aij. It is ith row and jth column of matrix, complete incidence matrix. It has the following values. So this entries. So we know that in the matrix we have this is the row. Suppose the n rows 1, 2, 3. N rows means n number. There are n number of nodes in the given network, or the branches, or in the oriented graph. Then this is the B number of columns. So how many branches are there in the oriented graph? So column represents the number of branches in the graph, and row represents the number of nodes in the graph. So this elements, so this is, suppose this is A11, this is A12, A13. So these are the entries. I will define Aij or A1. So if this branch J, if its orientation is away from the node I, this is the node I and this is the branch J. If its orientation is away from the node, so its value is 1, Aij. Suppose this branch is incident at node 1. So branch 1 is incident at node 1 and its orientation is away from the node 1. So its value will be 1. Here this branch A incident at node 1 and its orientation is towards node 1. So this is this branch J and this is the node I. So branch J is incidenting at node I and its orientation is towards node, so it will be -1. And the third case, this is the node and this is the branch. So this branch is not incident at this node, so this term Aij will be 0. So the entries of the matrix, incident matrix, will be 1, -1 or 0 depending upon the orientation of the branches. Okay. Now come to the another matrix that is related to the incidence matrix, is reduced incidence matrix, or simply we can say the incidence matrix. So there are two terms, complete incidence matrix, that is AA, and reduced incidence matrix, that is say A. Its notation is always A. This is A. So when one row of the matrix AA is eliminated, the resulting matrix is called a reduced incidence matrix, or simply an incidence matrix, and it is denoted by A. So it is an order of n-1 into B, whereas the complete incidence matrix AA is order of n into B, and matrix A, that is the reduced incidence matrix, is of order n-1 into B. So n-1 number of rows and B number of columns. So it is an usual practice to eliminate that row from the complete incidence matrix which corresponds to the reference of the network. Okay. So a network is given. So we just identify the nodes, reference node or ground. Okay, then we draw the graph of the network and we eliminate that row which is corresponding to the reference node of the network. So usually we remove the bottom one, the last row of the matrix. So rank of both A, that is the complete incidence matrix, and A, that is the reduced incidence matrix, is n minus 1. Now there are some properties of reduced incidence matrix. What are they? So the unit entries 1 or minus 1 in a row identify the branches incident at a node, and their number is the degree of the node. So if the two branches are incident at a particular node, then the degree of that node will be 2. If 1, then simple node. Then we have the isolated node also. Isolated node means no branches incident at that particular node. That node is called isolated node. So columns of A with entries 2 identical rows corresponds to 2 branches with same end nodes, and hence they are in parallel. So if the entries of 2 columns are same, then there are 2 branches connected in parallel. A degree of 1 for a row means that there is only 1 branch incident at the node, and this is possible in a tree. So a degree of a node is 2. It shows exactly 2 branches are incident at the node, hence the branches are in series. And this is the last one, is the this is the important to find the number of trees in a given graph. So just if the graph is oriented graph is given, draw the find the complete incidence matrix A, eliminate the last row from the matrix, we get this matrix A, then take the transpose of that matrix and multiply. So after multiplication, then find the determinant of that matrix. So that determinant of that matrix will give the number of possible trees in the given graph. So these are some properties of reduced incidence matrix. So in the examination, they may ask reduced incidence matrix, or they may ask simple incidence matrix. You have to identify. How will I identify? Because I am trying to suppose this is the given oriented graph of a network. Okay, and then we have obtained the complete incident matrix AA. Okay, so we can see that this is node 1, 2, 3 and 4. There are 4 nodes. Okay, and there are 7 branches. So we can see that this branch 1 is incident at node 2, and its orientation is towards node 2. So this it is between 1 and 2. So this branch is between 1 and 2. So this is node 1 and this is node 2. Okay, this branch 1 is between 1 and 2. So what will be the entries of this A11? Ij A11. So A11 will be 1 because this branch is away from this node. Okay, so it will be plus 1 for A11 and minus 1 for 2-1 because it is incident at node 2. So and the orientation is towards node 2, so it is minus 1. This is minus 1 and this is 1. So this one, then simply for 2 we can see that for this is 3 and 2. So branch 2 is in between node 2 and 3. So 2 and 3 we can see here. So It is incident at node 2, orientation is towards node 2, so it will be minus, and it is away from the node 3, so it is plus 1. Similarly, we can see for the third branch is in between 2 and 4. So 2 and 4, this and this. So 2 and 4. So it is away from the node 2, so it will be the plus 1, and it is towards node 4, so it is minus 1. So in this way we can obtain this complete incidence matrix. So from the network we obtain the graph, and from graph we obtain the complete incidence matrix. So in the paper, suppose it is written incidence matrix is given. So how will you identify whether the given incident matrix is complete or reduced? Just it is very simple. Just if the summation of interest, in a column is 0, if the summation of interest in a column is 0, then it is called complete incidence matrix. If it is not coming 0, then it is reduced. Clear? So summation of interest in a particular column must be 0. So we can see that 1 minus 1, 1 minus 1, 1 minus 1. So summation is 0. So it is complete incidence matrix. Suppose you want to write the reduced incidence matrix. So simply we just, this is A, and we take 3 nodes. So eliminate this one. Eliminate. So for A matrix, eliminate last row. This last row is this corresponding to node 4, and node 4 is nothing but it is the reference node of the network. So from the network is given, we can draw the oriented graph. From the oriented graph we can obtain the complete incidence matrix, and from the complete incidence matrix we can obtain the reduced incidence matrix. Now there are some terminology also associated with graph theory, that is the loop. So what is loop? So a loop or a maze or a circuit, all three terms are same, is a connected subgraph of a graph in which each node has a degree of 2. That is, exactly 2 branches are incident on each node of the loop. So between any 2 nodes of a loop there exist 2 paths. Okay, so this is the definition of loop. So in any loop the number of nodes must be equal to the number of branches. Then there is another term, that is the fundamental loop. So what is fundamental loop? So fundamental loop is applicable to a tree. So whenever a link is added to the tree, a loop will be formed. This loop is called fundamental loop. Suppose this graph is given, okay, and we have selected a tree having the branches 1, 2 and 3. So this is one tree of this graph. This is 1, 2, 3. Okay. If we add, suppose one link. So what is link? These are 1, 2, 3. They are called twigs. I am writing here 1, 2, 3. Then what are the links? 4, 5, 6, 7. They are called the links. So branches obtained in removing information of a tree is called links. Okay. So how many links are there? There are 4 links. The branches removed information of a tree are called links. So a fundamental loop of a graph with respect to a tree. So remember, the fundamental loop is defined for a particular tree. Is a loop formed by a one link and unique set of twigs. And fundamental loop is also called fundamental circuit, fundamental or tie set, and the number of fundamental loops are equal to the number of links. So how many fundamental loops are there? There are 4 fundamental loops. So we can hear. So if this is the 1, 2, 3, this is the tree. If we add one link, so we have one fundamental loop having the link 4. If we add another link, that is link 5, we get this fundamental loop. Then we add link number 7, we can get this fundamental loop. If we add link 6, we get. So there are 4 fundamental loops. So loops have orientations. So the orientation of the loop is same as its defining links. So orientation of link is this way, so it is the orientation of loop will be same. So the orientation is same as its defining links, coincide with the orientation of the link. Okay, we can see here. So by convention, the fundamental loop is given as the same orientation as its defining link. So branch voltage is positive with the branch orientation coincides with that of the fundamental loops. So we can apply the Kirchhoff's voltage law for the fundamental loops, and we can get this minus V1 plus V2. We can check it for all 4 fundamental loops. These are the equations. These are the loop equations. Okay. Then we can write these loop equations in matrix form. So we get this matrix, this and this one. So what are these? These are the V1, V2, V3, V4, V5, V6. They are the branch voltages. They are the branch voltages, and we have the this matrix. Okay. So we check, if you draw the fundamental loop matrix, we get this one. So this is called fundamental loop matrix. So this is this VF, VB is equal to 0. This expression we use in loop analysis. Okay. So where VF is L into B, matrix called fundamental loop matrix or tie set matrix, and is defined as this is. So BF is equal to Bij. So Bij, if the branch J is included in the ith fundamental loop and their orientations coincides. Bj Ij is equal to -1 if included in the ith fundamental loop, but the orientation is just opposite to its defining links. And if branch J is not included in the ith fundamental loop, then value of the 0. So with them in the matrix entry, we have the 1, -1 and 0. So the rank of the fundamental tie set matrix is B minus n plus 1. Now come to the another matrix. We have the fundamental loop matrix, other one the fundamental, other one the mesh matrix. What is mesh matrix? So if the graph is planar, there is an alternate way to selecting B minus n plus 1, means number of independent loops, and this is achieved by selecting meshes instead of fundamental loops. So in place of having the fundamental loops, we can have the meshes. So by definition, a mesh is a loop in which there are no branches in its interior. Okay, all the fundamental loops are called meshes. So it is general practice to orient all the meshes in either clockwise or anti-clockwise direction. So there are 2 approaches. One is your loop method, another one is the mesh method. In the loop method, we go for the fundamental loops, and the fundamental loops are as per the number of links. Okay, and the orientation of the fundamental loop is same as its defining links we have seen. But in the case of the matrix, the orientation of the mesh, for the mesh matrix, the orientation of the mesh will be either clockwise or anti-clockwise. All the meshes we can orient in clockwise fashion or anti-clockwise fashion, where we can see in case of the fundamental loop, some loops are oriented clockwise, some are oriented anti-clockwise. So this is the basic definition between the orientation of fundamental loop and the mesh. Now come to the another matrix that is called cut set matrix. So cut set matrix. So what is cut set? So cut set is a set of minimum number of branches of a connected graph whose removal causes the graph to be cut exactly into two parts, with the condition that by restoring any branch of the combination, the graph should be connected. So these are the cut set. If you remove 1, 4, 6, 7 from the graph is cut into two. If you remove this combination, the graph is again cut into two. If you remove this 2, 4, 5. So there are basically 7 cut sets which divide this graph into two, with the condition that restoring any branch of the combination, the graph is connected. This is another basic cuts the graph. Here we can see that 1, 2, 3 and 4, they are the twigs, and 5, 6, 7, they are called the links. So it is, here we can see that 4 branches are twigs and 3 branches are links. So we have taken a tree. So here we can see that there are only 4 cut sets. So in the earlier graph we have there are 7. Here we have only 4. So the basic difference is, for the fundamental cut set, how many fundamental cut sets? Number of twigs. If the in a tree there are 3 branches, so then 3 fundamental cut sets. If we have the 4, then the 4. So again, same as fundamental cut sets are defined for a given tree of the graph, and fundamental cut set of a graph with respect to a tree is a cut set that is formed by one twig and unique set of links. Whereas fundamental loops, one links and unique set of twigs, and the number of fundamental cut set is equal to the number of twigs. If there are 4 fundamental cuts, so 4 twigs, then 4 fundamental cuts. Now orientation of the cut set is chosen as its defining twigs. So this is the graph. Okay, then we have taken a tree 1, 2, 3. So 1, 2, 3, these are the twigs. 5, 6, 4, 6, 7 and 5, they are the links. So this is F1 corresponding to 1. So this is one cut set. C1 is one cut set having 1, 6, 7, 1, 4, 6, 7. Okay. So 1 twigs and unique set of links. Here this is your C2 and this is your C3. So 1 twigs, 6, 7, 5 links, here 1 twigs, and then we can write in matrix form. So Cij, these are the elements of the fundamental cut set matrix. If it is 1, if the orientation is same, if it is -1, if the orientation does not coincide the orientation of the twig. Same concept as we discussed in case of the fundamental tie set.
and Cij means elements of cut set matrix is 0 if the branch A is not incident on cut set J. So this way we can write this matrix. So we can see that the twig matrix, this is the twig matrix, this is the link, and the twig matrix is unique matrix. In case of the fundamental, if we check in the case of the fundamental cut set matrix, the link matrix is unique matrix. So this is all about your all the matrices that are being used in the network analysis, especially in the graph theory. That is incidence matrix or reduced incidence matrix we can say, then fundamental die-set matrix and fundamental cut-set matrix. So the procedure to obtain these matrices, if the graph network is given, the first step is network is given. Then what you have to do, if the network is oriented, good. Then if it is not, then orient the given network. Then from the oriented network, draw the oriented graph. Okay, the oriented graph. Then for the incidence matrix, count number of branches in the network and number of nodes. So if suppose there are n number of nodes, so there will be n number of rows in the matrix A, and if there are say b number of branches in the network, so there will be b number of columns in the matrix. And we can make the entries of incident matrix if the branch incident at node 1 and 2. Okay, suppose branch 1 is in between node 1 and 2, and it is if orientation of branch 1 is towards node 1, then A11, okay, it will be -1, and A12 it will be +1 because it is oriented away from the node 2. Okay, so this way we can fill up all the entries in the incident matrix. Come to the fundamental die-set and fundamental cut-set matrix. It is only defined for a particular tree. The tree is given. Okay, so tree is given, then we can find the twigs and number of links. So take for if you are going for the fundamental die-set, then take the tree, add one link. Okay, we get one fundamental loop. So add all the links to the tree, we get the number of fundamental loops. Then the next job is to just to orient the fundamental loops. How will you orient? As per its defining links. So orientation of the fundamental loop is same as its defining link. Come to the fundamental cut set. Tree is given. If not given, then take tree. Okay, then remainings are linked, and 3 branches are twigs. So for fundamental cut set, we take one twig and unique set of links and cut the graph, and the orientation of the cut set is same as its defining twigs. And this way we can obtain the matrices, and these matrices are very useful in loop analysis and node analysis. Basically, for the loop analysis, we use your fundamental die-set matrix, and for node analysis, either we go for the incident matrix or cut set matrix. So thank you very much.